Okay, let's have a look at the next example. So the next example is a bit of a trickier one, but it's in the same spirit of what I said before. So I'm going to take a nice real problem and I'm going to solve it using complex numbers. So what I want to do, I want to find the exact value of sine pi on 5. So I could type sine pi on 5 in my calculator, but that will give me a decimal, which is an approximation, and that's not what I want. I want the exact value of sine pi on 5, and this seems completely unrelated to complex numbers, right? Because it's a real problem. It's not imaginary at all. But I'm going to show you how you can solve it using complex numbers. So I put a little bit of a hint in the question. I've said that let z to be cos pi on 5 plus I sine pi on 5, and evaluate z to the power of 5 two different ways. So I put that there in case if you want to give it a go before you watch me do it, like with all the other problems I said. But let me show you how it's done. So now, if I want to calculate z to the power of 5, again, there are two ways I can do it. There's the Markways theorem and there's the binomial theorem. So if I use the Markways theorem, right, then z to the power of 5, so because the modulus is 1, it's going to be 1 to the power of 5, which is 1. And because the angle is pi on 5, I'm just going to multiply that by 5, which gives me pi. So I get cos pi plus I sine pi. Now sine pi is 0, cos pi is minus 1, so this comes out to be minus 1. If I use the binomial theorem, okay, then cos pi on 5 plus I sine pi on 5 to the power of 5. Okay, so if you're not familiar with the binomial theorem, don't worry about it too much. It's not really the focus of this video. I'll just write out what you would get if you do apply the binomial theorem. It's just the formula which you can easily look up online. But if you apply it, you get this. Sum from k equals 0 to 5. 5 choose k. You could write like this, cos pi on 5 to the k, and then I sine pi on 5 to the 5 minus k. Okay, so then what you do is you just expand this. So you literally just sub in the values of k. So if you put k is equal to 0, you get 5 choose 0. Now cos pi on 5 to the 0, that's just 1, so you forget about that. And you get I to the 5, sine to the 5, pi on 5, like that. And then you just keep on going. So you put k equals 1, 5 choose 1, cos pi on 5, I to the 4, sine to the 4, pi on 5. Put k equals 2, 5 choose 2, cos squared pi on 5. So you can see how tedious this is. Really makes you appreciate the theorem. I cubed, sine cubed, pi on 5. So what am I up to? K equals 3. 5 choose 3. Cos cubed pi on 5. I squared, sine squared pi on 5. K equals 4. 5 choose 4. Cos to the 4 pi on 5. I sine pi on 5. And when I put k equals 5, the sine term of course disappears. So I just have 5 choose 5, cos to the 5, pi on 5. And I can simplify this, right? In terms of the choose calculations, I can just do that on my calculator. And in terms of the i's, well, I know I squared is minus 1. So I cubed is minus I to the 4 we know is 1. And I to the 5 is just I. I think we spoke about that at the very beginning. So if I do that, and if I do the choose calculations on my calculator, I get I sine to the 5 pi on 5 plus 5 cos pi on 5 sine to the power of 4 pi on 5 minus 10i cos squared pi on 5 sine cubed pi on 5. minus 10 cos cubed pi on 5, sine squared pi on 5. So 2 more terms left, plus 5i cos to the 4 pi on 5 sine pi on 5, and finally cos to the 5 pi on 5. Right? I get this. Now notice what's happened. I've evaluated z to the power of 5 two different ways, and I got two different expressions. I got this, and I got all this. Now if you think about it, logically they have to be equal, because they both equal z to the power of 5. So that big thing that I circled, all of that equals negative 1. So what that means is, in order for that big expression to equal negative 1, we'll first note that technically both of these expressions are complex numbers, right? So minus 1 is technically a complex number. Its real part is minus 1, and its imaginary part is 0, and that big expression is a complex number as well. I can separate the real and the imaginary parts. Now, in order for two complex numbers to be equal, their real parts have to be the same, and their imaginary parts have to be the same. So, the real part of minus 1 is just minus 1, and the real part of the big expression, to see what the real part of the big expression is, we just look through it, and we ignore any terms that have an I in it. So for example, the term 5 cos pi on 5 sine to the 4 pi on 5 doesn't have any i's in it. The term minus 10 cos cubed pi on 5 sine squared pi on 5 doesn't have any i's in it. And likewise cos 5 pi on 5. Now the imaginary part of negative 1 is just 0, and the imaginary part of that big expression, we just look for all the terms that have an imaginary, or just the I term in it. So it's going to be sine to the 5 pi on 5 minus 10 cos squared pi on 5 sine cubed pi on 5 plus 5 cos to the 4 pi on 5 sine pi on 5. Now I need to make some more space to continue on the next page. So let me just copy this so I don't forget where I was up to. So copy. I'm gonna. Whoopsie. Okay, so I got all this, right? So this is where we're up to. So I have two big equations right now. Now what I can do with this one, to be honest, I don't really need the first one. That was just to demonstrate for you how to equate real and imaginary parts. I'm going to work with this second equation. So if I take this second equation here, notice I can divide through by sine pi on 5, right? Because there's a common factor of sine pi on 5 on the right, and obviously sine pi on 5 is not going to be 0, so I can divide through by that, and that's going to give me sine to the 4 pi on 5 minus 10 cos squared pi on 5 sine squared pi on 5 plus 5 cos 4 pi on 5. Now keep in mind that I'm trying to solve for sine pi on 5 here, so that cos is in the way. I can get rid of that cos using my trig identities, because we know cos squared is 1 minus sine squared. Okay? To make this a little bit less messy, let's make a little substitution. I'm going to let u to be sine squared pi on 5. So sine to the power of 4 would essentially be u squared. Now cos squared would be 1 minus sine squared, or 1 minus u. Sorry about that. Sine squared is just u. Then 5 cos to the 4. Well, cos to the 4 is cos squared squared. And we know cos squared is 1 minus u. So we get this. And then if we expand this out, okay, if we expand this out, we get 16u squared, and we're going to have negative 20u plus 5. And now this is a quadratic, which we can solve using the quadratic equation. So it follows that u, which remember was just sine squared pi on 5, if I apply the quadratic formula, so if I apply the quadratic formula, you just to skip the calculations to save you some time, you end up getting this, 5 plus or minus root 5 on 8. And so therefore sine pi on 5 has to be plus or minus square root of that. Now obviously that's not the final answer, right? Because currently I got 4 different values, 4 possibilities for sine pi on 5, but we know there can only be one, because it has to be unique. Now, in order to figure out which one is correct, we'll first note that pi on 5 is in the first quadrant, and we know that sine is positive in the first quadrant, so I can't have a negative square root, because otherwise that would imply sine pi on 5 is negative, which wouldn't make sense. So here we say that since pi on 5 is in first quadrant, right, we have to ignore the negative. So sine pi on 5 is going to be square root 5 plus or minus root 5 on 8. Well, now the question is, within the square root itself, do I take the plus or do I take the minus? So that's a little bit tricky to see which one to do. The argument I'll show you is I'll show you that if we take the plus, it leads to a contradiction. Because if sine pi on 5 equals 5 plus root 5 on 8, then what's going to happen is that sine pi on 5, right, you can say that this is going to be greater than square root of 4 on 8, because 5 plus root 5 is bigger than 4. The numerator is going to be bigger than 4. This in turn is 1 on root 2, which in turn is sine pi on 4. So that would imply that sine pi on 5 is greater than sine pi on 4. And that makes no sense. That's a contradiction, right? So the reason it's a contradiction is because we know that the sine function is increasing when you go from 0 to pi on 2. No space. When you go from 0 to pi on 2. So sine pi on 4 would have to be bigger than sine pi on 5. So if you assume the positive, we get a contradiction. So therefore we must have the negative. So therefore we must have sine pi on 5 to equal square root 5 minus root 5 on 8. And again, I reckon this is a very nice problem because what I've done, I've found the exact value of sine pi on 5 using, and even though this is a real problem, I've done it using complex numbers. So this is kind of what I was saying before.